Yo. What's up? Welcome back. Today we're working on my operating system. It's called Stream OS for now. Puns are welcome. Pun suggestions welcome, I should say. And this is just like a x86 operating system. It's written for fun. There's no real goal. We're just kind of like trying to poke and prod, see how operating systems work, and maybe use that as a way to learn about computers, programming, a way like maybe build an intuition about how real operating systems work, etc., etc. But really, if we're gonna be honest, like it's just because it's fucking fun. Yeah, so where we're at right now is we have an operating system that it boots. It has like vectors, maps, it has memory allocation, it has like some form of concurrency, it has serial logging, unit testing, where logging goes to like standard output when I run through a virtual machine. It has like a pretty shitty clock and like a Ethernet stack so that we can render a web or serve a web page, do like TCP stuff, UDP stuff, etc. We have like some like shitty form of graphics where we can like draw pixels to a frame buffer, and we have keyboard input handling, so that we can like control things in our games, etc. What we're working on right now is multi-core support. So as of right now, our whole operating system kind of works under the assumption that we are running on one core. And as we're working towards enabling the other cores, fixing all of the assumptions about one core, and trying to run our like task executor in like a multi-threaded way so that it pulls tasks from whichever core is free to do work, and we'll run it there. Yeah, so where we are working in right now is, okay, let's see, symmetric multiprocessing OSDev. So in order to boot a symmetric multiprocessing system, which I think is just the fancy word for all cores do similar amounts of work. They're all similar strength. They have like same memory space. Maybe that's not part of the symmetric multiprocessing definition, but that's like my understanding of at least my setup. And in order to do this, they need a handle to this thing called like the AIPC, which is the Advanced Interrupt Controller. And in order to get a handle to this, we need to parse this thing called the MADT, multiple APIC description table, right? Because there's going to be one per core. These come from, let's see, ACPI tables, right? And these tables come from this thing called the root system description pointer. And this thing comes from multiboot 2, which is like this boot standard that like Grub implements. So like if you're like ever booted Linux, you boot and you get this like little menu of like, oh, you can boot Ubuntu right now. That's Grub, and Grub does a bunch of like the like pre-initialization stuff. So when my CPU boots, it's in like 16-bit mode because like 30 years ago people ran DOS in 16-bit mode or something, and like when they released 32-bit processors, they didn't want to like fuck up the 16-bit stuff, so they're like, okay, we'll like start in 16-bit mode and you upgrade. So the bootloader handles that upgrade for us. It also handles a bunch of like interaction with the BIOS, because a bunch of the BIOS stuff can only happen in 16-bit mode, if I understand correctly. So what we do is we like ask the bootloader Grub to do all of this like initialization and like asking the BIOS like what's plugged in and like what features do I have and how many CPUs do I have. All of that comes from BIOS calls or UEFI calls on newer systems. And we basically are saying like, hey Grub, you do that for us and we'll implement this like multiboot 2 spec and you just give us that info. And so that's what we're working on right now, is implementing multiboot 2 support. We originally on our first boot, we implemented multiboot 1 support because it was easier, and I think probably like when you just go like, how do I boot an OS? OSDev wiki, please tell me. I think that's where it started us. And so now, yeah, we're going through multiboot 2 stuff. So last year we got pretty far. We got to the point where everything was working the same after boot, except for our frame buffer was not getting initialized. I'm sorry, we actually initialized the frame buffer, but we had trouble we didn't ever get the handle to the frame buffer from within our OS. So that's what we're working on now. Let's just quickly checkpoint here. And let's see if we can like quickly get into a state where we can show the current features. So I think if I cargo run right now, without GDB, oops, it's actually already running. This boots, it initializes a 640 by 480 window. It does some like demo stuff where it says like, hey, look, we have a vector, we have a map, we have like date time, and we modify the date time in the RTC, and we can get our MAC address from the Ethernet card, and we can like find the MAC address of another PC on the same network, and we can sleep. And if I set up netcat, I can like say hello, and my OS receives the word hello and it sends it back. So like everything's kind of working. But we used to have a game in this window, and that's not working right now. Yeah, so where we got to at the end of last stream was we thought that we were like debugging why we weren't getting the framebuffer info. So the idea behind multiboot 2 is they give you a header that has like, sorry, how do I say this? On operating system boot, they put a pointer in one of your like registers on the CPU. And if you look at the pointer there, you get like a pointer to the structure. Maybe we start drawing it. Right, so in your like CPU, you have like this register, EBX, and he's like a pointer to some memory. Okay, and in here we have like this multi-boot structure. Which has, this is probably not it. This is the requester side. Here we go. Which has like a size. And then he just have like, then he has like a list of tags. So we have each tag will have like ID, size, and data. And this block is going to happen like n times, so this is going to be copy pasted like here, 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 right, until we run out of room. And each one of these tags has like different stuff in it. So what we're trying to get to is we're trying to parse this like frame buffer info one. And our current state is that we never find a tag with type 8. And last stream, we were kind of like printing out what we got here. So here we're saying like, oh, we have tag 21, tag 1, tag 2, tag 10, tag 6. And then we get into the state where after we do tag 6, we have this like tag 5539. And that looks like very clearly wrong, right? We don't have 5,539 different types of things that we could do. And we have one that's like type 0, size 27. I think type 0 doesn't even exist. If we look type equals 0, we don't see that at all. Yeah, so we were getting a point where like we're clearly making a mistake in our parsing here. And so that's what I wanted to look at today, is trying to like fix this, get a handle to the frame buffer, fix the frame buffer stuff so we have feature parity with when we were booting with multiboot 1. And if we get there in a reasonable time, then probably the thing to do is start trying to like work towards getting a handle to the ACPI tables. Yeah. That's it. So let's kind of just get moving. Okay. So here clearly, so how do I say this? We've kind of validated that the memory map that we're getting from multiboot is working. This is like a list of memory regions, one of which is like our entire memory space. And last stream we validated that if we increase the total size of memory that QEMU, our virtual machine, provides our operating system, we do see that number in the memory map kind of like match up with what we're providing. But the thing after that is just like totally fucked. And so it's possible that when we're parsing this like size field for each of the tags, we're kind of going like, read the size, jump to the next one, read the size, jump to the next one, read the size, jump to the next one, depending on what the size value is. And it's possible that it's wrong, that memory is corrupt, or that we are parsing incorrectly. And this parsing incorrectly is like the most likely thing because we don't know what the fuck we're doing. We've just kind of like opened this doc and started typing without even really reading it all the way. So I think that's where we want to look here. So the way this works is in our multiboot 2 stuff, this is our iterator. Yeah, and all we do is we have like a location that we start at, an end location, and we check if we hit the end. Yeah, so, and then we check if there's like maybe there's a null terminator tag as well, which also we exit on. So when I was just scrolling this multiboot 2 thing, like literally just now, I did notice that they have some sample code here. So I do want to see what they do here. So here they have total size comes from the multiboot header, and then they iterate over tags. So they say tag is equal to adder plus 8, while tag type is not equal to multiboot tag end. We tag is equal to the current tag plus the size plus 7 and inverted by 7. So this is how they 8-byte align their thing. And I am now realizing that my version of 8-byte alignment is just fucking wrong. Oh, okay. So what I did here was I tried to say size mod 8 is going to be like some number between 0 and 7, right? And I tried to say like, well, if size mod 8 is equal to 1, then I should like add 7 to the thing to make sure that we're aligned to addresses 8. So I did 8 minus size mod 8. That's great, except in the case where size is 0, we're going to increment by 8 for no fucking reason. And so what these guys did is just the more correct thing. And they're saying that size plus equals we say size equals size plus 7 and Boolean not of 7. And what this is going to do is we're going to say if size is 0, we're going to get if size is, how do I draw this? Say we have like, okay, what this is a mask of 7 is what, 0xf? No. Okay, calc. Does this show me in bits? No, it doesn't. Okay. We'll boot up Python then. Python 3. So we'll say format this as Boolean, and we'll print 7. So this 7 is 111. Right? So we're saying that these are the bits that we want set, or that we want to clear, right? And anything from 0 to 7 is invalid because we want our pointers to be 8-byte aligned. So what we do by saying this not 7 is we convert this to, what the hell? Is it not 7? No. Well, basically we convert like 0b111 to 0b111111111 followed by 3 zeros at the end, right? The number of ones here isn't relevant. It's just that like all of the, like we're masking out the top section of our value. And here we add 7 so that we are always in like the worst case. Yeah, and I think that kind of works out. So let's see if that fixes everything. Hey, there we go. So these types are now reasonable. Okay, and now we are in fact getting our frame buffer info, which is great. And we are moving and grooving. Very nice. So here we'll say that we fixed size tag size alignment bug. Okay. And so now we're going to parse frame buffer info. And it would be nice if we could see all this. We're going to make this like guy stuck in the maze a little smaller, a little stretched-er, a little more stretched. And here we go. Okay, so what's next? Next is now we're actually getting frame buffer info. And so here we can fix this. We'll panic here and we'll say failed to get frame buffer info. In reality, maybe we should just return none here, right? It's because so that our operating system still runs without a frame buffer. And here we'll say we return an option frame buffer info. And now we actually have to parse this guy. So what would be kind of fun here is if we just print them out. So we'll say print line I. So let's see what we get here. And we'll say frame buffer info is this. Here we need to fix this guy. None of this matters. This does. So this is frame buffer. Okay. Cool. So now we do in fact get a frame buffer info, and he's got a type 8, he's got an address, he's got a pitch, he's got a width, he's got a height, bits per pixel, frame buffer type, our red, green, blue stuff. And I am noticing that I think that this is equally incorrect as it was in our multiboot 1 implementation. So back when we set up this like frame buffer stuff, we did notice that the positions don't match in real life what we actually see. So we ended up swapping red, green, and blue. And it looks like, if I remember correctly, I think that we have to do that same hack again. So what I'm going to do is I'm actually just going to copy paste all this shit out of the frame buffer 1 stuff. And put it in the multiboot 2 stuff and kind of see if it lines up. Okay, so here we're going to say return some this. And this is no longer self, so what do we have here? In multiboot 1, we converted the color size from bits per pixel. Oh, our size looked wrong. So that's the first thing that we have written down here, is that the sizes didn't all line up. And this is true again, right? So red is 0, but the red size is 16. That doesn't make sense because we have 8 bits per pixel. Oh, no. Hold on. No, this still doesn't make sense, right? So I was going to say that this would kind of line up. The 16 kind of makes sense if they have a 32-bit thing, but it's like 24-bit. If it's supposed to be 24 bits, but we have 32 bits of data so that it's like aligned on a pointer axis, we might have like red takes 16, like this. Green takes 8, blue takes 8. So we'd have like R G B. But these offsets don't align with that, right? So like the fact that the green field position is 8 and the blue field position is 8 is like, what the fuck are they talking about? And the blue mask has 0. So let's actually read the spec again and see if this actually makes sense in the multiboot 2 world. Let's check that. So here in the multiboot 2 spec, let's look at the frame buffer stuff. So frame buffer BPP is equal 16. Frame buffer pitch is expressed in bytes per line. Yeah, okay, let's see if we can find somebody who's using this. Red mask size. Nope, Yeah, there's something wrong here. So we're gonna ignore these values again for now, because this doesn't line up, right? Because this says here that we have red field position 0. So if this is 0, with a mask of 16, but then the green position is 8, so that would be here. And then we also have a blue field position of 8, which doesn't make sense. I wonder if we're actually have these inverted in some way. Right? This would make a lot more sense if the blue field position was 0, the green field position was 8, and the red field position was 16. So if we were like off by 1 byte, this would be 16, 8, 8, 8, 0 something. Ooh, so that could be it. If we're off by 1, that would make sense. So let's see if we can kind of try to prove that to ourselves. Because that'd be nice not to have to do this like fucking hack. So what I'm going to do is I'm going to go into GDB, and I'm going to set a breakpoint at this line. And I guess I'll just sit there at that point. So let's relaunch our OS, but with GDB. And what happens here is like QEMU sets up a GDB server for us, and then we can like connect our GDB instance to it and start debugging memory, which is a pretty sick feature, honestly. Okay, so what do we have? We have p star I, and so if I look at this guy, we should have the type is the first thing in here. Yeah, so if type is 8, that lines up. And does our frame buffer type line up as well? Frame buffer type should be 1. Great. And then reserved is always contains 0 in the current version of the spec. So here we have do frame buffer type, reserved 0. Okay, so let's look at the address of this guy. So I think it's address of info dot frame buffer red field position. Okay, and let's just start printing out this, like, let's just print out like 7 bytes here. So let's see, what do we have here? So we have 0, 16, 8, 8, 8, 0. So this would make sense. It was 16, 8, 8, 8, 0, 8 for red position, green position, blue position. Right, because then the mask sizes are all 8. So it's possible that like this color info is off by 1. So let's try to look at that. So is there anything... Color type is defined as follows. It's 6 U8s. Or is it possible that we're off by 1? So if we shifted our reserved by 1, then everything would line up. Let's look at our like type definition here. So our frame buffer info. Does he line up? U32, U32, U64, U32, 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 U8, U8, U8. Then this like varies. So let's see what the size of this guy is. Can we like maybe print somewhere the size of the frame buffer info grid? So here we can say core mem size of, and we say frame buffer info priv. And the reason I'm doing this is I want to see if we are off, like out of bounds, or sorry, if the like size of the struct doesn't match the size of the object, basically. So here we get the frame buffer info size is 40. And what do we get for the size of the actual tag? So here we have, here, can we just print out the type and size again? So we'll say print line, type is type, and size is size. Target run. I guess we don't need GDB for this test. Okay. So that's fucked up. Right, we get size 38 is what we detect, but we think it's size 40, and we're not aligned right? Did I make a mistake? So this is 8, 16, 20, 24, 28, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. Wow, we're all over the place here. 4, 8, 16, 20, 24, 28, 9, 30, 31. 2, 3, 4, 5, 6, 7. Okay, so maybe we have to pack this. So that now matches up, 37. And does this stuff match up? Red field position 0, red mask size 0. This is still fucked. Right? Like, we know that the red field position is 16. And that the mask size should be 8. So I wonder if we just make our reserved a U16, which doesn't match the spec. Do we get something much more reasonable? Red field position 16, red mask size 8. Green field position 8, green mask size 8. Blue field position 0, blue mask size 8. Like, that's just like much, much, much more correct. But like that's true. That's what we've like determined is correct in the multiboot 1 version of this. And our size is 38, which matches what GDB said. Or sorry, not GDB. Matches like what the header of our thing says. So I don't understand. Something here is like just fucking wrong. Okay, so what I'm going to do here is I'm just going to say, note that spec says reserved should be 0. However, when I parse the color info, these values make sense and are correct. And with reserved of U8, it's total trash. We'll say it's inconsistent with itself and incorrect. Okay. Let's just delete all of these comments here. I'm sure there's there's a bug somewhere, but we'll just live with this for now. That's fine. Which makes this implementation of converting into our public version of this that we export is going to be much easier now. So let's go back to where we do this, and we're going to return something like a initialized structure. His color size is going to be... what do we do in multiboot 1 here? I think this is in bytes instead of bits for some reason. I think that I just thought that'd be easier. This is still reasonable, so we take the maximum of RGB. We should probably actually just assert that they're all the same now. So we can say assert that equals... what do we have here? I dot... Hello, where is it? Red mask size is the same as I dot green mask size, and red is the same as blue, and then we return color size is I dot red mask size. Great. Okay, what else do we have here? We have red mask size. Oh, this should be frame buffer red. Oops. Like this, we throw a frame buffer in there. Oops, I added a space. Get rid of that shit. Oops, I didn't mean to get rid of that either. So then we have green field position. So now these are right. Were my offsets in multiboot 1 in bytes or in bits? They were in bytes. So here our red offset is I.framebuffer red field position over 8. This is blue and this is green. And here we need to assert that each of these guys is mod 8. So here we have red, green, and blue. Okay, now we have bytes per pixel is just going to be 1. Or sorry, no, this is frame buffer BPP divided by 8. And here we also want to assume that frame buffer bits per pixel mod 8 is 0 because we're working in bytes. Our width is I frame buffer width. And the pitch is pitch. And the height is height. And the address is frame buffer adder as u8. All right. Very nice. And so it's possible that this is just going to work now. I guess somewhere we have to actually call this and get it back. So all of the places in main where we commented out the frame buffer, we actually are going to have to like look at it now. So let's go back to main and let's see. In kernel init, we're just going to do this. Which means that here we're going to do frame buffer is equal to frame buffer info. This guy is using frame multiboot 1, and we're just going to change this to multiboot 2. Everything else should just work the same. Except that we have to check if we actually get it. So if let some frame buffer info. We'll just expect it for now. Failed to get frame buffer info. There we go. So now we're just going to uncomment all the places where we commented with the frame buffer. Here we can bring the game back. And we can use the game here. And let's see if that actually runs. There we go. Very nice. So we're back at feature parity. Very cool, very cool. I'm happy with that. So frame buffer is now up and running. Now there is a little bit of an issue where we did see last stream that the like frame buffer info is kind of how do I say this? It was in the memory area that like could be seen, like, how do I say this? The memory allocator could, in theory, allocate memory that overlaps with this frame buffer info stuff, or like the multi-boot info stuff. But for now, I'm not going to worry about that, because that was a problem before as well. So let's add u, get add dash u, get commit dash m checkpoint, multi-boot to boots successfully with feature parity. All right. Very cool. So here we'll say that we fixed brick breaker game with multi-boot 2. Very nice. And now we're working on some cleanup. Clean multi-boot 2 stuff. Because probably we did a lot of like shitting the bed here. So one, we can remove multi-boot. We don't need this at all. Right, we're only on multi-boot 2. We'll cargo check here. In main 57, we're trying to use something that we don't need, and in allocator, we're also trying to use some stuff that we don't need. Multi-boot 1, great. When we're passing our allocator the like multi-boot stuff, we're kind of initializing the multi-boot 2 thing directly here, which we shouldn't. We should pass in the multi-boot info here as a multi-boot 2. Which means in main, we call allocator init. We should pass in a multi-boot info. Which should actually come from the interrupt guard. We should do this like all the way up here. So here we'll pass in like this, great. And now info here is a multi-boot. Multi-boot 2, and the allocator init comes with the multi-boot 2 info. Great. We'll just call this info here. Everything else just works. Cool. Here we can pass in info, great. And I think the only other thing here now is to fix this guy. Now we don't have to construct him twice, but we do move him. So we'll just fix all of these guys to take him in by reference, because he doesn't actually need to be moved here. Great. Borrow check. Oh, he needs to consider a borrow here. Of course, of course. And we cargo check. Great. Cargo format. And can we cargo Clippy? Is there anything that the linter is complaining about? Actually, surprisingly not. We'll maybe do a little git commit here. And let's kind of see what we left our history looking like. So I think I'm okay with just folding everything down here. And let's see what we've done since the last commit. So we edited our QEMU wrapper to add 512 megs of memory. We don't need to do that. We can leave it how it was. So let's look again, backup 1. So we switched our grub config to multiboot 2. I don't think that was required. Well, it might have been. Let's try it. Let's see. So if we go to grub config, we say, please boot with multiboot 2, but really we could have just multiboot maybe, and grub maybe is smart enough to figure it out by looking at the binary. Let's see. No, he actually does need the multiboot 2. Otherwise he doesn't boot. All right. Works for me. So this guy says multiboot 2. Let's run him again and just double check. We're up and running. Great. What else do we do? Our allocator, we added some like printing to it, and we don't need that, so let's back that out. So that was here. We added start and end. We added start and end. We added print range, and somewhere we probably set the start and end on initialization. Here. Cool, so that gets all the allocator stuff out. We probably need to clean up our boot.s stuff a little bit because some of these tags that we were using before aren't really needed anymore. So this was like multiboot 1 stuff that we don't need. The flags are no longer part of it. Instead, we like pass in these tags directly. This magic is still the same, but the checksum is no longer this. And here we can probably put these guys just down here. Constants at the top seems fine. Sure. So this is the multiboot to magic. And in reality, maybe we should like name this a little better. So we can say multiboot to magic. And here, let's change this to multi-boot to architecture. Great. This is still true. The bootloader will search for the signature in the first 8 kilobytes. The code, blah, 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 blah. Sure, yeah, this is true, except we should just say that this is the multi-boot 2 stuff now. Checksum is still reasonable. Size set to 0. Grub doesn't care. This is the framebuffer tag. This is correct. Terminator tag. This is also correct. Okay, I'm happy with that. What else did we do? Our framebuffer stuff uses the multiboot 2 stuff now instead. Our main has like slightly adjusted how he works with the multiboot stuff, but he also calls allocator print range, which no longer exists. This init looks fine. We've converted this to a const-u8 instead of taking a pointer to the multiboot info directly because we want to parse it ourselves as we construct it. That's fine by me. Framebuffer stuff looks very slightly different, but it doesn't really matter. And what do we do here? Oh, sure. Our kernel init now takes the multiboot magic as well, so it can validate that we're booted with multiboot 2. And everything in here is pretty reasonable. I'm okay with all of this. Okay, cool. So let's quickly just amend this and say, what? Switch from multiboot to multiboot 2. And why? Why are we doing this? As we prepare for multi-core support, we need a handle to the, what did they call it in this like giant list of jargon? RSDP, which is the root system description pointer. This is how we get a handle to the advanced programmable interrupt controller, which is required for multi-core setup. Multiboot 2 gives us the descriptor we need. Multiboot 1 did not. Upgrade to multiboot 2 without losing any, without making sure that we have feature parity. Great. Very nice. All right. So I think if I run my lint scripts, that should pass. Nice. Oh, we do have a bunch of print lines in there that we should have actually removed. So this is in, probably in the multiboot 2 stuff. I didn't really look closely enough here. Status, get add you, get commit amend, cargo, run the lint script again. No bullshit prints. And we run. And everything's up and running. Cool. So we are now in a state where we can push. So let's merge this in. Quickly make sure that it's good, and we'll push. And the remote side is going to quickly validate that this compiles and runs before pushing, or accepting the push. And this is our kind of like shitty version of CI, where instead of asking like GitHub actions to validate our code after we push it, we just like on our machine, we're pushing to a file, like a folder on our file system that's mirrored to GitHub. And he just says, hey, if I can't build and run these tests, or if like my lints fail, like fuck you, I'm just gonna like reject your push. Yeah, but that's pretty cool. So let's try getting the ACPI stuff out of here. Let's try it. So in the multiboot 2 spec, we can have the ACPI old RSDP or the new RSDP. I don't know what the difference is. Let's see. So here he added extended descriptor. Which seems reasonable. Is the extended descriptor like much more difficult? Let's look here, maybe. So what does he look like compared to the old version? These look very similar. I think that those are identical, actually. However, there are many kinds of SDT. The header which is come to all SDT for each table is this. So it's probably the same shit where we have like a list of elements and we go element by element or something. Let's see. So how do I parse this guy? He gets the header and he goes for each element in length. He looks at some. Oh no, that's not it. He has pointers to other tables. So he has his header and then pointer to other SDT. How to use. Suppose I want to find the FADIT. The FADIT, being an SDT, has an ACPI SDT header. Its signature is FACP. Ah. Okay. So for each element in here, we look at the pointer to the other descriptor table and we check its signature. And if the signature is the table that we want, then we know. Okay. So it does look like, if I'm understanding like this chunk of code correctly, we have memory, and in each slot of memory, each of these segments here are going to be XSDT is the root. So where's the struct XSDT come from? Here. So each one of these guys is going to have the header inside, which is this stuff. And okay. So here we're gonna have like header, and then after that he's gonna have like a series of pointers. And each of these is going to point to another header. So he's going to point to like basically another copy of this guy. He's going to be here, here, and here. And the data is going to be based off of like what signature we see there, probably. Okay, that seems reasonable. So I guess what's like a reasonable thing to do here? A reasonable thing to do would be to print the signatures of all the other tables that we see. And that's like a really good like intermediate point where we could say, wow, we actually like got something of value out of this. So let's try to do that. Which means probably want to have like a new area of code. Let's call it ACPI. And in main, we'll just include this module. Cool. And oh, I guess sorry. The first thing we have to do is in our multiboot 2 stuff, we actually have to get a handle to the ACPI root descriptor table. So this whole thing started because we weren't sure if we wanted version 1 or 2. Let's do version 2, which means that in our tag iterator, we are looking for tag 15. And here it's going to return some tag of what? RDSP2. Which is going to have a whole copy of the RSDP, not RDSP. So here we're going to have item as const RSDP2 tag. Probably is a good name for this. Which means that we have to like actually make this tag. So this is RSDP? And this is a RSDP2 tag. And the reason I'm throwing tag on here is because we're going to put this actual RSDP somewhere else in the ACPI stuff. And so this guy has a size, or type, size. He needs to be repr C. He's a type and a size. And copy of RSDP. What the fuck? That's crazy that the BIOS does DHCP. Wow, that's kind of neat. So, like, in theory, I could, like, get an address in my operating system without ever implementing DHCP just because the BIOS implements it. That's fucking crazy. Or not the BIOS, the bootloader. Well, that seems like an insane thing for the bootloader to do. Am I crazy? For the bootloader to, like, have an Ethernet card driver? Oh, sorry, I misread this. Okay, so I was thinking, like, that would be nuts. If the Ethernet, like, if the bootloader had to have every single Ethernet card driver and do a DHCP thing, but instead it's just saying, no, that's still crazy. Even if this is like not for an actual DHCP response, and it might just be like configuration info, that's still nuts for it to be able to interact with the network cards at all. What what a large responsibility for the bootloader to have. I must not understand this correctly, so I'm gonna ignore that for now. But if I get that, that's crazy. I would maybe this spec is maybe a little much. Maybe I have to like request. Yeah, whatever. Maybe that's wild. Sorry. Okay, so here's a copy of the RSDP here. So here we have the RSDP2 tag. This guy needs to implement debug. This guy has to be like this. And the rest of him is going to be what? He's going to have the RSDP. Well, we'll just say value or descriptor is just going to be an RSDP2. And now we go into ACPI and we struct RSDP2. And then here, this needs to be a public struct, and this guy has to implement him. So we'll say, what? Use create ACPI RSDP2. Okay. So this guy has to be repr C, and oh, this is actually, everywhere I used RSDP, I need to say RSDT. Oops. Why is it called RSDP in some places and RSDT in others? Oh. RSDP and RSDT are different. Okay. Okay. Sure. So what is in this RSDP? Version 2, it looks like this. So we'll just yoink. And yoink. And what? This is 1, 2, 8, 9. This is going to be wrong. This needs to be packed, I think. Or else the alignment won't work out. And here we just, what do? We make a vim macro where we delete this word, we swap the case here, the case here, we go to the end of the word, we put a colon, we paste the type again. Ah, fuck. Okay, undo that. Undo. I made a mistake. Okay, new vim macro. Delete a word. Swap case. Go. Ah, fuck. Vim macro. Delete word. Swap case. Go to the end of the word. Put a colon. Paste the word. Swap the semicolon for a comma. All right, that's close. Now we just have to fix these guys. This is a U8, and this is a U8. This is a U86. This is a U8. This is a U32. This has to have an underscore here. This is a U32, this is a U64, this is a U8. Great. And then this guy also has reserved is a U83. So let's double check this now. This is 8, 14, 15, 16. So this actually doesn't have to be packed because it is aligned. Great. Let's derive from this debug. And let's fix this and this to be snake case, and this should be comma. Cool. Cargo format, because that's butchered, fixes everything for me. Nice. And now, I guess we'll just do the same thing here. We'll say, we're gonna call this what? Get RSDP. This is going to return RSDP2. Probably, I don't know. And if this is RSDP2, we'll print line it for now. For debugging purposes, but later we're gonna actually use it. And in main, now, in our like kernel init or something, we can just print it in the RDSP. So we'll just go down here. And we'll say info get RSDP. Cargo check. Do we build? Nope, because we spelled something wrong. Here we said itemy instead of item. Great. Cargo check. Cargo run. Do we get something interesting out of this? So he never printed it? That's weird. I guess we never saw this tag. So I guess we actually do have to go back to our tag iterator here. And what I'm going to do actually, just for fun this time, is instead of adding prints here, I'm actually going to go in here, set a breakpoint in each of these, and say for each breakpoint, print, where was I looking here? I'm going to say, I guess I want the breakpoint to be here. What line 105, and I can say print the type and print the size. And continue. And then if I run this with GDB, it's kind of fun. I just get to, yeah, look, that's pretty fun. So for each of these, I get to print it. So I'm looking for a new RSDP, type 15. We can even get a little crazier. And say dprintf type integer size integer, and I think you can say like tip size. I think. I think it's like this. So I say make a breakpoint at this location with this string with these arguments, I think. We'll have to double check this. It's been a while. It's been a while. So let's do GDB equals 1, Carter run the GDB script, format string required. So I think maybe I have to put commas here instead of spaces. Format man dprintf. Help dprintf. I want it to work because it's so cool. Location, format, string, arg1, arg2. So we have location, format, string. Maybe I have to get rid of these spaces or else it gets mad. Ah, there we go. There we go. Hey, isn't that kind of fun? So without actually recompiling anything, we do get these like kind of like nice printf style things in the debugger. I've always thought that was kind of fun. So I'm noticing that none of these are type 15. Right? We do have type 14. So I guess I just don't have ACPI 2. That's kind of surprising. So can I look up QEMU ACPI 2.0? There's always OVMF. So it might just not support it. Ah, so it uses CBOS, which is too old. Okay, okay. So after all of that, after deciding that I wanted version 2.0, fuck it, we don't have it. All right. Okay, okay, okay. I should have checked that earlier. That was stupid. I should have checked. So we're going to take out all these 2s. And then I'm going to go to the ACPI stuff, and I'm going to take out all this. This guy doesn't have a 2 anymore, and this guy doesn't have a 2, and this guy doesn't have a 2. We're going back to RSDP1, baby. Here we have a 2, so this should be this, and this should be this. And somewhere down here I have RSDP2, so this should be RSDP1, this should be RSDP1. And instead of 15, we're looking for 14. Oops. Can I write volatile that requires the pointer is... Oh, that's weird. Is this because of GDB? Okay, so we are on the bright side. We do have the RSDP. Is the signature correct? RSD pointer. 8-byte string, not an alternator. So I guess we should convert this to a string and take a look. So down here we can see, is this valid? So we'll say what? P dot header, was it? What do we say the value inside was? Descriptor. And signature, and we'll just say core stir from UTF-8 unchecked. So let's just see what if this guy says what he's supposed to. And this is a private field, fine, so you can just kind of like fuck off, pub, great. And here we need to borrow, sure. Okay, so this is good. We are seeing RSD pointer like it says we should. I am curious about where this right volatile unaligned is coming from, so let's kind of take a look at that. So I think that what we can do is we can go to our main and look at our panic implementation. And here, just put a breakpoint here. So we'll say run.gdb, breakpoint at this. And then when we run with gdb equals 1, let's see, we look, the other thing I want to do actually is I want to support reloading. So we're just going to say like del br here. Okay. So gdb-x run gdb. Okay. So where's this coming from? This is coming from game clear screen set pixel. Oh, that's interesting. Why all of a sudden is our frame buffer not aligned? It was a second ago. There's probably a mistake in our like packing somewhere. I bet you if I run release, this works. Which means that here I need to edit my GDB script to use the release version. Yeah, so there's pointer alignment issues in debug only. Either there's pointer alignment issues in debug only, or we're only checking for pointer alignment issues in debug. I actually don't know which one it is. Okay, but that's something to come back to. I wanna put that on the back burner because I want to keep going on this like RSDP stuff. Okay, so we've parsed the RSDP. We can check the revision field, which we should assume is 0. But I guess if we don't check the field and we get like version 2, but we think it's version 1, that'll probably still be fine actually, because I assume version 2 is backwards compatible. Before the RSDP is allowed upon, you should check the checksum is valid. You add up every byte in the structure and make sure the lowest byte of the result is equal to 0. So you add up every byte in the structure and make sure the lowest byte of the result is equal to 0. Oh, I see. So the checksum is just a value that will make that true. Okay. Oh. This is supposed to be packed, according to this. So let's go back to RSDP and let's actually put a packed on here. And I do actually, while we're throwing packed on stuff, I guess it does make sense for us to throw a packed on this guy. Oh, he is packed. All right. We might want to just like put a packed on everything in here, but whatever. We'll come back to that. I was trying to avoid looking at the framebuffer stuff, but I can't help myself. I can't help it. I can't. We'll print the address in both debug and release, and we'll see. So we'll see if these are the same. If they're different, then there's something like really wrong. Otherwise, it's fine. Well, not fine, but we'll think about it. So here we get FD0000 in release. We get the same address in debug. That's really interesting. It's really interesting. So let's maybe see if we can. Oh, I can't help myself. I can't help myself. We have to debug it. We have to. We have to. So let's look at the GDB thing script. We put this back in debug. We have our panic thing set, so we can just probably gdb-x, run our script, backtrace, look back to this right volatile, and see what we're actually trying to do. So that's frame 6, and we can say, what address are we writing to? That's definitely not aligned. Okay, so why the fuck is that happening? So let's look at the code here. So here we're saying adder is something offset. So p offset 3. P row, p self.info.pitch. That's crashing for some reason. $19.20. What else is happening there? P self.bytes per pix. What the fuck? 128. That's fucking wrong. Bytes per pix is 128. Whoa, 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 whoa. Whoa, 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 whoa. Okay. So we run, we source, run.gdb, we print i.framebuffer bpp 24. So that should be 3. It could be that, like, sometimes when you, like, get into these, like, panic things, sometimes, like, the stack doesn't restore itself correctly. Is the frame buffer supposed to be packed? Is it, how do I say this? I thought that when I saw this before, I thought we were doing 32-bit values, but packed into 24-bit depth, but I guess not. So, I guess we actually do have to do something more like, we can't write the whole color at once. Unless in our boot script, can we ask for 32-bit depth? Maybe? Does that build and compile and run? So what do we get here? Okay. So we get 8 bits per pixel. Let's hit continue and see. All right, cool. So that's just like a little bug there that we accidentally made, where when we asked for 24-bit color depth, it was doing the wrong thing. But it was like giving us 24 bits of color, which is like the same as when we have 32 bits, except they were 24-bit aligned. 24, yeah, which is 3-byte aligned, which makes like the efficiency of using this a lot worse. So if we ask for 32-bit depth, it'll still give us 8 bits per pixel, but it'll align on 32-bit boundaries, which makes like the writing colors much nicer. All right, cool. Okay, so we aside fix bug in frame buffer pointer alignment. This is 011326 and don't know when we started. Okay. So we're back to trying to read the pointers, the root system description pointer. So we want to do checksum validation. So in multiboot, probably maybe in sorry, one sec. In the ACPI stuff, we can do maybe impl here, and we'll say function validate checksum. And I guess this will return a bool, and we'll say For b in self.sig, self, this takes in self, obviously. So we iterate over the signature, and we say let ac equals 0. And instead of, I was going to iterate over each field manually, but instead I'm actually going to cast this whole thing to a byte array. So we'll say let pointer is equal to rsdp, or I guess self, as const u8, or I guess as const rsdp. And then we say p is p as const u8. And then we say for I in 0 to core mem size of rsdp, we say ac plus equals p dot add I, and we dereference. Here, great. And I guess we call it, we're going to say that this is a 0 U8, and we're going to say that this is a wrapping add. Great. And then here at the end, we can just say ac equals 0 is if the checksum is valid. So now somewhere we can say RSTP, so probably in the multiboot stuff for now. We somewhere try to get the RSTP, and we're just going to say print line p dot validate checksum. And we'll say here checksum valid is this. Really? This is p dot descriptor validate checksum. And this is a private method, so we have to make this public. Great. And then we can cargo run. We don't need GDB anymore. Let's just see what we get. Attempt to add with overflow. Right, so... Oops. This should be act.wrapping add this. Oopsies. Whoopsies. Okay, so checksum is valid. We are big chilling. So now we can look at the RSDT address, and that will be the address of the RSDT. Okay, so what the fuck is an RSDT? Here is the RSDT header. And what happens in case you use RSDT pointer? So we have signature, length, revision, checksum. Okay. Then we have the OEM ID, revision, creator ID, creator revision. Okay. Here we go. This is the same shit, actually. This looks very similar. So here, their RSDT, it has pointers after the header to the next one. So this is like a linked list. We don't have XESDT. We only have the shitty version. So, okay, cool. So this is easy. So let's try to print every single header signature. So here we pull this guy. And we do our vim macroing again. So we delete a word, go to the end of the word, paste the type. Fuck, wrong button. So we vim macro, delete a word, go to the end of the word, colon, paste type, replace the semicolon with a comma, and we do that for all these. And here we go all of these, and we say we want them to be lowercase, and this is OEM ID, OEM table ID, OEM revision, creator ID, and creator revision. This type we need to convert uint32t to u32, uint8t to u8. car to U8, and this is a U8 as well, and we need to fix these array types. So Rust arrays look like this, so like this, and this doesn't need semicolon. Okay. So we also probably need to repr C and pack this shit, so that it matches the format in memory, like precisely. Okay. And now, we can do this. So here we have this guy. So here's the header is like this. And then here he has pointers, is a unknown length array. So I guess this is just a, we'll call it a U32. And in our implementation for this guy, we'll make a function called, what? We'll call it print headers for now. And he's going to take in himself. He's going to say, let length, it's equal to self.header.length. I guess we don't have to do that. And then we'll say, let pointers is going to be self.pointers, but he's, instead of going to be a U32, he's going to be an address of the U32. And I guess we're going to say, for I in 0 to length over 4, because the length is in bytes, not in whatever this is. Oh, we're going to say p.add I, dereference that. And we'll say let, what, child pointer is equal to this. Yeah. This needs to be as const U32. And this needs to be usize like this. Probably. This is unsafe, so we stick an unsafe block, sure. And we cannot divide U32 by usize, so it's actually like this. Very cool. Okay. Okay. So then what are we going to do? We're going to try to get the signature from each of these guys. Yo, what am I working on? Okay. So there's a little bit of a rabbit hole here. We're trying to enable multi-core support. And to enable multi-core support, we need to get a handle to a advanced programmable interrupt controller. And to get the advanced programmable interrupt controller handler, we need to parse these like ACPI tables, which are like this like cross. I don't know whose standard it is. I think I saw like Tush. What? It's here somewhere. Standard. Intel, Microsoft, Toshiba made this standard, which is like basically your way of like enumerating hardware, kind of. So like the BIOS will like give us this table. And it will like tell us things like how many CPUs we have, where I have like interrupt controllers, where I have blank, like there's just like a bunch of like things that it'll tell us about as far as I understand. And if you like are on Linux and you go and look at like sys ACPI, I think that you have like, there's just like a bunch of shit in there. It's like power management protocol as well as like hardware enumeration. So what we're working on now is enable to get multi-core support. We are trying to parse the ACPI table so that we can find the programmable interrupt controller handle so that we can turn on the CPUs. And right now we're just trying to prove to ourselves that we can, in fact, parse this ACPI table and at least get like a list of useful strings. Okay, so for each of these children in the table, we're going to convert this to a pointer to an ACPI header. And let's just print the name of like let's just fucking print the signature. So we can dereference this and look at the signature, and let's just print line core format from UTF-8 unchecked because I don't really give a shit if it's wrong. And this should be core stir, actually. There we go. And here I need to borrow this guy, like this. Okay, so now I just have to like actually get this RSDT from the RSDP. So I guess it's like a pointer to the table, and here we have the address. So probably in my multiboot stuff, we can say let RSDT is equal to the descriptor.rsdt address as a const pointer to an RSDT. And then we can say rsdt.print headers. And let's take a little peek-see. So here we need to import RSDT, which is private. So we need to go into the ACPI stuff and mark it as public. Oh god, you're such a nag, Rust. I get it. You want me to be safe, but fuck off. Okay, here we go. And now we cannot print this without dereferencing this guy. Okay, and there's like a very good chance that this just fucking crashes, but it'd be cool if we just got a list. Yeah, so here we're already fucked. So we're doing a misaligned pointer dereference. That's probably this guy, so maybe here we just say repr c packed. I should have done this from the start. I didn't realize I hadn't. Reference to packed field is unaligned. Packed structs only aligned by one byte. Blah blah blah. So here I actually should. Does that actually just not build? How do I assert that this is aligned? Is there like a is aligned, or can I like? Oh, does it just not let me do this? If I say that this is a U8, fuck off. Packed structs are only aligned one byte, so I guess just we'll write that this isn't packed, and just hope to God that this works. But it might not. There's like a good chance it doesn't, so let's see. Misaligned pointer dereference, fuck off. Okay. So how do I make sure? I guess maybe I can make this a null type and pass this to this guy and say let p is equal to p as const u32. Okay, that gets me somewhere. That is still gonna crash. Okay, so now let's actually start running with GDB, and we can start seeing where we're going wrong. So run.gdb, and where are we crashing? We are crashing in print headers as expected. And here it's p.add_i as star. Sure, okay, so that makes sense. This is an ACPI line 56. Is there a goal with making this OS? Not like a concrete one. I think that generally I find it easier to learn about stuff by doing it, right? So like, yeah, if you write something, you're gonna understand it pretty well in the same way that if you like explain something to your friends, you must understand it better than if you just read it and thought you understood it. It's kind of fun, good stream content. I've always wanted to, yeah. So, all of that kind of saying that like we don't really know what this OS is going to turn into. We're just going to kind of like just make stuff and see where we end up. Yeah. Okay, so here I've got a misaligned pointer dereference, frame 3. So let's look at what am I trying to do here again? I don't even remember. Fuck, I can't back on this. So this is p.add_i as const list. So okay, so let's see. We have p dot sorry, I have to foreground %2, so this will work. What's I here? I is 0. P is this. Whoa. Oh, oops. Okay. So already this doesn't look right. So this table, I'm supposed to have this header, then a uint32 array of pointers to other SDTs. Where I have h.length minus size of h over 4. So I've already kind of fucked that up. I didn't do this. But this pointer list should be walkable. I guess if the ACPI SDT header, how many bytes is this? 1, 4, or 1, 5, 6, 7, 8. Oh, fuck. 4 plus 4 is 8. 10 plus 6 is 16. Then this is all 8-byte aligned. So this should be 8-byte aligned. Where is like RSDT here? EA. So is that 8-byte aligned? No. I see. So our whole descriptor table is not aligned, which means that we can't just access these as pointers. Ugh. That's annoying. That's annoying. All right. So I guess that's reasonable. So here we're gonna say that this is like pointers goes like this. So for each of these, instead of dereferencing these directly, we have to say we can't dereference it, but we can mem copy it out. So we can say let pointer or child u32. This is child pointer is equal to a mem copy of this out. So how do I do that? I think I can p. So I have the child pointer as const u8. I copy this out. So I say what? Core mem copy. Transmute copy. Interpret source as having the type desc, then read source without moving the contained value. Maybe this is what I want. So here I have a what? Oh, maybe I just use memcopy. I think I have kernel create libc memcopy, and I can say let child u32 is u30 equals 0. And here I can say the destination is child u32 as const u8. Oh my god. And the source is child pp as const u8, and n is 4. Here I need to make this mutable, and this needs to be mutable, and I have to actually cast this to a mute u32 first. Okay, and so now I should be able to look at this. So we should be able to say let child p is equal to child u32 as const ACPI SDT header. God damn, that's complicated. Let's try this again and see if the misaligned pointer accesses go away. Hey! That's pretty sick. Look at that. We have, these are like valid signatures. Very cool. We're still broken, right? Because we're crashing, but let's take a look. So we're getting a lot farther. We're actually getting at frame 15 at ACPI 60. Which is coming from panic, unwind, slice iter, into iter, right string. Yeah, so there's something with this from UTF-8 unchecked. So probably this length has to be -1, or length. Oh, this is just fucked. Length as usize. This is length minus something. Self dot size of, I think, core mem size of ACPI SDT header. There we go. And this should be length as usize minus this. Okay, let's see if that fixes it. Let's fucking go! That's so sick. Okay, so we have in fact iterated over all these ACPI tables, and we are seeing what is WAET or HPET? Let's see if each of these is valid. So APIC is definitely the one we're looking for, right? We're looking for the advanced programmable interrupt controller thing. FACP is this guy. What is HPET? Oh, high precision clock. Oh, fuck yeah. I wanted to get this guy too at some point. Sick. And then what's WAT? Windows ACPI emulated device table. Woo! Okay. That's pretty sick. I'm happy with that. I think that's enough for me for now. I think I'm pretty happy with that. Right, if I was going to keep going, I'd go for like another 20 minutes probably. And I don't really think that I have anything that I want to really accomplish in those next 20 minutes that's like short enough. So yeah, I'm pretty happy with that. I think probably tomorrow we can keep going, and maybe we'll go on the API pick, or maybe we'll look at the high precision timer, because I have been kind of noticing that the 4 millisecond tick rate is not very good. And when I was reading some of the multi-core initialization stuff, I did see that like we do need a more precise sleep than that probably. So I think next stream we'll look at either the high precision timer or the advanced programmable interrupt controller. Today we got pretty far. We got to the point where we started from multiboot 2 headers not being properly parsed. We fixed our multiboot 2 parsing. We got feature parity with our multiboot 1 implementation. And so then we started reading the ACPI tables that are provided to us by multiboot 2 to the point where we know that we're at least like finding the tables that we want to see. Yeah, so I'm pretty happy with that. If you liked what you saw, you can always tune in. I stream most days on Twitch around like 1 or 2 Pacific time for like 1.5 to 2 hours. And if you miss stuff, you can always catch up on YouTube. YouTube is linked in the Twitch description. And if you're watching on YouTube and you want to pop in and say hi, feel free. Twitch description is linked in the YouTube description. Yeah, so thanks for watching. Catch you in the next one. Bye!